and I'm starting the streaming on YouTube's side. Alright, I can see the YouTube side is okay, it's working. So we got about 2 more minutes before we need to get started. So this is more, it's not really a question, but I just want to let Daniel know that, if you think that I can do things a little bit differently, let me know. I don't know how well the way I'm lecturing is lending itself to captioning. And let me start to screen share on Discord's side. There we go. All right. I'm gonna mute myself as I drink my coffee because otherwise you guys will be hearing all that slurping sound. Alright, so we got about a minute to go. And what we'll do today, just a quick preview of what we are doing today. So what we'll be doing today is to go over the resolution logic, basically why it works, okay, why the mechanism works. And then the second thing we'll need to do is to kind of redefine CNF, redefine well-formed formulae a little bit to make use of conjunctive normal form. And then after that, we'll move on and there'll be some examples, and then we'll move on to talk about proof by contradiction. So all of these pieces are connected in order to make it possible for a computer to prove theorems using propositional logic. So that's what we'll be doing. Alright, so it is time to get started. As I said a little bit earlier, what we'll do today first is to go over the resolution mechanism itself. Basically we want to look at a proof to basically see how why it works. My mouse pointer keeps disappearing. Even though I can ping it, it doesn't reappear, which is really kind of annoying because I can't see my mouse pointer. Okay, that's okay. Um, Just trying to think of a way to see if that can be. Alright, so let's see, would that help? Oh, okay, I think I saw something. Oh, there we go. Okay, I found my mouse pointer again. Alright, so let's take a look at this derivation because even though we have not formally introduced Boolean algebra in this class, which we will very soon, like today, but we would like to kind of take a look at how this works. So the first thing I do in this case is to get rid of the implication operator, and this we have talked about already. So the implication is basically the negation of the left-hand side or the right-hand side. So that's why you see the negation of the left-hand side of the implication. So this entire conjunction is on the left-hand side, and then we have an or, and then just simply the right-hand side. And then from here to here, I applied De Morgan's law, and we'll talk about De Morgan's law later today. So De Morgan's law basically allows you to quote-unquote distribute a negation into a conjunction or a disjunction, into the inside of the conjunction of a disjunction. So that's actually pretty useful. Oh, okay, I'm just looking at the homework assignment request. Sorry about that, I didn't see that earlier. Okay, so let's go back and take a look at the relation homework. And I'm gonna do my own version. Alright, so there we go. Question number 1, consider the not equal to relation over all integers. Which of the following relations properties apply? So I think it really is going to be helpful if you can kind of remember what these properties means. And the best way to do it is to look up my definition in the class, because the quantified expression is really kind of how I look at all of these properties. The first one is symmetric. Not equal to is symmetric. So symmetry is not really that big of a deal, because what it means is if A are B, if and only if B are A for all A and B in the set. Okay, so that means if one exists, the other one has to, and then if one does not exist, the other one cannot exist. So that that's basically symmetry. And not equal to is really quite obvious that it is symmetric. Like 1 versus 1, well, 1 does not relate to 1 using not equal to. So either way, it doesn't go. But for anything where A and B are different, then A does not equal to B, if and only if B does not equal to A, that works, because it does exist in in both directions. We cannot easily directly answer partially ordering, because we have to because partially ordering relies on anti-symmetric, transitive, and also there's one more, reflexive. Okay, so we have to look at reflexivity here. Reflexive is pretty easy too, because reflexive means something relates to itself using the relation that we are talking about. And for not equal to, it is quite obvious it is exactly the other way. So we'll basically say it's not reflexive. If it's not reflexive, it cannot be partially ordering already. So we know it's definitely not partially ordering. So let's look at transitive. Okay, it's not equal to transitive. The answer is it is not transitive, because I can say because with the transitive you need 3 variables. ARB and BRC implies ARC. Okay, which has nothing to do with the college. Okay, I'm just using A, B, and C as variables. So in this case, you can choose A to be 1, you can choose B to be 2, and then choose FC to be 1 again. So in that case, it doesn't work, right? Because A does not equal to, 1 does not equal to 1, is not true. So we know it is not transitive. So the tricky one is the other tricky one, because transitive is a little tricky, but the other tricky one is anti-symmetry. Okay, is it anti-symmetric? Anti-symmetric means if you can find ARB and BRA, then A equals to B, which is obviously not true in this case. It is definitely not anti-symmetric. So as a result, for question number 1, it really is just 1. It really is just option number 1, which is it is symmetric. All right, moving on to question number 2. And I'm just checking the Discord to make sure it's still active. There we go. So question number 2 is using equal to instead of not equal to. So with equal to, it is symmetric. Okay, so if 1 equals to 1, then 1 equals to 1. Yeah, so that's pretty obvious, right? It is definitely anti-symmetric because because ARB and BRA, if implies A equals to B, is definitely true. Okay, because an element can only relate to itself using equal to, so that's definitely true. And it is also transitive, because if you can find 1 equals to 1 and 1 equals to 1, then 1 equals to 1. Basically, I use 1 for all 3 variables in that formula. So it is definitely transitive. Is it reflexive? Yeah, you betcha it's reflexive, right? Every element relates to itself using equal to, which makes it partially ordering for sure. But it is not totally ordered. It's not totally ordered because things only relate to itself. Everything is only related to itself. But in order for something to be totally ordered, everything has to relate to everything else, including itself. Okay. But in either direction. Okay. So ARB or BRA has to apply to every single way to find A and B as elements of X. So it's not totally ordered. So for question number 2, it is all of the options except for totally ordered. All right, moving on to question number 3. If R and S are both relations defined over X, and we also know that R intersecting with S is reflexive, then what do we know about R for sure? Okay, so that's the question, and the only thing we really know is it is reflexive, nothing else. We don't know whether it's anti-symmetric or not. There's no way to tell whether it is symmetric or not, but we do know for sure it is reflexive. So for question number 3, it is just that R is reflexive. And for this one, it's not. I could have made it more tricky by turning all of these into check boxes instead of radio buttons, because for radio buttons you can only choose one. Once you know that, hey, I know for sure it's going to be reflexive, then that's pretty much the answer. But if I made these into check boxes, then it gets a little bit hairy, because then you really have to think about, well, can it be, do we know for sure it's going to be transitive? Do we know for sure it's going to be anti-symmetric? So that gets a little bit more interesting. Question number 4 is less than. Okay, so we want to look at less than, and we don't want to determine the totally or partially ordering first, because those rely on 3 of the other properties. So the first one is whether it is reflexive or not. Definitely not reflexive, right? Every value cannot be less than itself, so it's definitely not reflexive. Let's check symmetry. Okay, definitely not symmetric, right? Because if A is less than B, then B cannot be less than A. So it's definitely not symmetric. Is it anti-symmetric? Strangely, it is anti-symmetric. Okay, I'll explain that in just a little bit. So I'll check this one. Or if you guys think, yeah, we got that, okay, then I'm not going to talk about it. So in the text channel, you guys can say, whether you understand why less than as a relation is anti-symmetric. Okay. And then for transitive, it is definitely transitive. If A is less than B and B is less than C, then A is less than C. Kind of makes sense intuitively. Okay, so the only one. Okay, so let me get back to the total versus partial ordering first, and then I'll go back and explain why it is anti-symmetric. Right. Okay, so it's not partially, and therefore it is definitely not totally ordered, because both of those require reflexive. So since less than is not reflexive, so we can rule out partially and also totally ordered. So now let's get back to anti-symmetric. Alright, so I'm switching to the tablet. Okay, let me see where my tablet screen is. or it has, oh, there we go. There we go. And it's sleeping. Because, you guys remember, how, if text classes are boring, then people will be sleeping and then they will feel rejuvenated. Apparently, my tablet agrees, and it slept. It was sleeping a little bit earlier. There we go. Um, okay, so we want to look at antisymmetric. Antisymmetric. There we go. And we want to recall the actual expression, where, if the expression is true, then we can call a relation over x, r over x, being antisymmetric. So we can say r over x is antisymmetric if and only if, okay, because this is a definition, so we gotta use if and only if, because one is, if one is true, the other one is, if one is false, the other one is also false. So the equation, which I hope you guys would have not really memorized, but to have it understood at this point. Memorization is pointless, okay, because you all the exams are open book and open notes, and this is the way it is even before COVID-19, because I truly do not believe that we should be using our neurons for rote learning purposes. I mean, that's just a waste of neurons. But I do want to make sure people understand the concept. So the concept, or let's look at the equation first, okay, the formula. So the formula says, I might be using some different symbols now, but, it's the same concept, okay? So we say for all a, b in x. So that means, for any way of picking a and b as elements in x, they can be the same, they can be different, it doesn't really matter. So we're considering all possible ways of choosing elements in x. We want to have one element bound to a, we want to have one element bound to b. They can be the same, they can be different, it doesn't really matter, okay? So what really is important is the expression, the Boolean expression inside the parentheses, because this is what we require regardless of how we choose a and b as elements of x. Okay, so in here, we want something like this, okay? So we want a, rb, and b, ra to imply a equals to b. That is the equation. I might have used a different notation, like I might have used the two tuple notation in my notes, which is ab in parentheses in r, right? That's the same as saying arb. A relates to b. So I might change the notation a little bit here, but they are equivalent notations, and this one is definitely more concise. Okay, so now we look at this conjunction, because if this conjunction is always false, then we don't have to worry about whether a equals to b or not, because if this conjunction is false, because this conjunction is also the precedent of the implication, which means it is to the left-hand side of the implication. If the left-hand side of the implication is false, what happens to the value of the implication itself? I want you to answer this question. You can answer the question just inside your head to yourself, or you can type your answer in the text channel, but this is what I want you to think about. Okay? What happens when the left-hand side of an implication is false? What happens to the value of the implication as an operator? And Garrett got it right. Okay, it becomes true. So now we look at ARB and BRA. What exactly is R? R is less than in this question, right? So can you find me two values, two integers, a and b, such that a is less than b and b is less than a? It doesn't work, right? Because with integers, you can only find one to be less than the other, but it cannot be, because it's not symmetric. It is not symmetric. So that means when we get back, let me not get back yet. Okay, so that means this expression is always false for less than. So if that is the case, that means the implication is always true. But if the implication is always true, that means the relation is in fact anti-symmetric. So that is why. Cool. And now we move on to number 5. Consider the greater than or equal to relation over integers, blah blah blah. Okay, because it's always asking which of the following relation properties apply. The first thing is it is not symmetric. Okay, it is not symmetric because if you choose 4 and 5, okay, 5 is greater than or equal to 4, but 4 is not greater than or equal to 5, so it's not symmetric. To show that something is not, when you have a universally quantified expression, all you have to show is, hey, I find this one case that can make the Boolean expression false, okay? And that's all you need in order to make the universally quantified expression false. To make sure it's true is a little bit harder, okay? But to make it false is super duper easy. Then let's move on to something easier first, like reflexive. It is reflexive, okay? Because if is every integer greater than or equal to itself? The answer is yes. Okay, it is greater than or equal to itself, so it's definitely reflexive. And just like less than, intuitively we understand that greater than or equal to is transitive. If A is greater than or equal to B and B is greater than or equal to C, then A is greater than or equal to C. So that intuitively makes sense already. Okay, so now we move on to something that is trickier. Is it anti-symmetric? What do you think? I mean, we just looked at the anti-symmetry definition, which is this one here, and I'm going to erase the false because in this case, it is not always the case that this is false. In other words, we can find certain cases where A is greater than or equal to B and B is greater than or equal to A, but that happens only when A and B are the same. Think about it, okay? A is greater than or equal to B and B is greater than or equal to A. That does imply A and B are the same. Does that work? Okay, so intuitively it works, but let's do this using Boolean algebra, okay? Because today's part of today's emphasis is Boolean algebra, which is kind of like algebra except the rules are slightly different, right? So we want to look at this and go, okay, we kind of know that this makes sense intuitively, but can we prove it, right? For all possible integers A and B. So let's do this, okay? It's actually easier than you think it is, okay? So we'll say A is greater than or equal to B and B is greater than or equal to A is really the same, equivalent to, okay, A is greater than B and A equals to B. Oops, not and, cannot be at the same time, or, there we go. And B is greater than A, or B equals to A. Okay, does anyone have any question about this line, like why we can expand it a little bit? I'm gonna drink my coffee, and this time I'm not turning off the mic, but I want you guys to think about this a little bit, okay? Does that make sense to you? I don't see any questions, so I'm gonna assume that it does make sense. All right, cool. So just like in algebra, you have FOIL. In Boolean algebra, we have FOIL as well. So that means if you look at an OR like an addition, and you look at an AND like a multiplication, FOIL works just like exactly the same way as regular FOIL. So now we can have the 4 pairs, right? A is greater than B and B is greater than A. Okay, that's the first component of the FOIL. And then we have A is greater than B and B equals to A. That's the second one. And then we have A is equal to B and B is greater than A. And I need extra parentheses here, okay, because we need to first operate on the conjunction first. Just the operator priority would actually imply that is the case, but I want to make this like really clear that we are performing the conjunction first, and then all the results of all the conjunctions are ORed together. And then the last one is A equals to B and B equals to A. So that really is kind of the long way of doing FOIL, right? Because it's really long because each component of the FOIL is a comparison between A and B. So now what do we do? Something doesn't seem to make sense. A is greater than B and B is greater than A. You're right, it doesn't make sense. It is false. What about the next one? A is greater than B and B equals to A. That doesn't make sense. I mean, if A is greater than B, then B cannot equal to A. If B does equal to A, then A cannot be greater than B. False, right? So all the conjunctions are false except for the last one, except for this one over here. This one is indeed, true when A and B are the same. So this entire thing reduces to A equals to B and B equals to A. And then now you can just apply your normal algebra that basically says, if you don't need to emphasize that A equals to B and B equals to A. You can just simplify it to just A equals to B. There we go. So that's the Boolean algebra way to prove that A is greater than or equal to B and B is greater than or equal to A, implies that A equals to B. Okay, well, nobody is typing any questions, so we are good to go to the next question. Oh, right, I'm not done with this one yet. So it is antisymmetric, and since it is reflexive, antisymmetric, and also transitive, so that makes it also partially ordered. Okay, so that's nice to have. So now the big question is it also totally ordered? Because every integer has to relate to another integer using this relation. Now the direction can go one way or the other. Okay, that's a flexibility, but we do make sure that it does relate in one way or another. And the answer is yes. Give me any two integers, I can arrange it so that one is greater than or equal to the other one. Alright, so that means it is also totally ordered. So that answers question number 5. Now we move on to question number 6 and 7, which have to do with the cardinality. Can we know anything about the cardinality comparison if we know certain things about the relation itself? Alright, question number 6 is asking if R is a relation defined over X and it is known to be reflexive. Which of the following do we know for sure, regardless of the actual definitions of R and X? Alright, so the only thing we know is it is reflexive. Alright, so let's check this out. We know R is less than X, or the cardinality of R is less than the cardinality of X has to be false. So don't even bother with this one. They can be equal, okay, if R is reflexive and nothing else, okay. Well, actually, if it is just barely reflexive, it is the minimum relation just to be reflexive, then they are the same. But nothing here says that it is just reflexive or minimally reflexive. So that is not the case. Not equal to, possible, but also not 100% always. And greater than or equal to, this one we can buy. We just know the cardinality of R is greater than or equal to the cardinality of X because we know every element relates to itself, but we don't know what else is in R. Okay, because the question says, hey, R can be anything. The only thing we know is it is reflexive. So that's the answer of question number 6. And now we move on to question number 7. If R is a relation defined over X and R is known to be symmetric, which of the following do we know for sure, regardless of how R and X are defined? This one is a little trickier. Okay, are the cardinalities do not equal. Mm, I can make them equal, right? How do we make it equal? Easy peasy, because we know an empty relation is symmetric. So it has a cardinality of 0 regardless of what x is. Let's see. So Aiden says for this one, is there some relation of r and this squared, the cardinality of r and the square of the cardinality of x? Okay, so an r can only the cardinality of r can only be as big as the square of the cardinality of x. So that puts an upper bound on it, and that's for every single relation, right? So so the relation is, yeah. So bar x bar squared is greater than or equal to bar r bar, um, is always true, regardless of any relation, regardless of any property that we have claimed that we know about the relation. Yeah. So if I put an option here, then you just check that one, because that one is true regardless of what r is. Okay, second option. The cardinality of r is exactly the same as twice the cardinality of x. That is not true, right? Just knowing that the empty relation is by itself symmetric already rules out the second option. I don't even have to come up with an example. And someone can say, but Tech, you just came up with an example of the empty relation. But we talked about the empty relation when we talked about symmetry. So this is not new. I did not invent this example just now. This is knowledge. Okay, this is not an application of knowledge. This is knowledge because I talked about this in a lecture. Okay. All right. Next, the cardinality of R is even. That seems to kind of make sense, right? Symmetric, even, symmetric, even, symmetric. They seem to be related, but no, they're not. They're not, because I can have just one element relating to itself and no other relationship between any elements, and that relation is symmetric, and yet the cardinality is 1. Okay, so that throws out even. Exactly. And then we have less than. Okay, nope, we can definitely make it equal to. Okay, because if you think about a relation that is just barely reflexive, then it equals, right? And a relation that is barely reflexive with no additional elements in the relation has the same. The cardinality would be the same. Okay, it is odd. No, I can make it even because an empty relation has a cardinality of 0, and 0 is an even number. So we can rule out that one too. They are the same. No, because I can have a barely reflexive relation and just add one. Let me see. No. I can have a barely reflexive relation and then subtract one of the elements. It will still be symmetric, but the cardinality won't equal to anymore. And also the empty relation is also symmetric, and that basically rules out the equality right away too. Greater than or equal to? No, because of the empty relation. So just knowing the fact, okay, that the empty relation is symmetric, not even knowing why, okay, we have already ruled out many of the options here. So the answer is none of the above. Yep. There's only one question here that uses none of the other answers can be confirmed, and this is the one. All right. So let's take a look at my score, because I should be getting a perfect score. Yes, I did. Okay. Well, sometimes I make mistakes and then I go like, darn it, I tricked myself. My past self tricked my present self. Kind of like I think that would be a great episode in Doctor Who, is to have a past Doctor Who to trick a future Doctor Who. Yeah, I know. Many people are probably not a Whovian, but I am. All right, time for more coffee so I can increase the pace of the class. Okay, so what is the requirement of totally ordered? The question is, I don't quite truly understand why equality is not totally ordered. So what is the one extra requirement of totally ordered when you compare that to partially ordered? Yep, it has to be comparable. And what does that mean? If I were to write a quantified statement of comparable, what would that look like? You don't have to use LaTeX here, just kind of give me the main part of it, right? Yep, exactly. So given any two, okay, ARB or BRA, they can be both, okay? It's okay to have both, it's not a problem, but we need at least one of them, right? So if I just pick two random integers, like 2 and 3, okay? If I pick A to be 2 and B to be 3, can I say A equals to B or B equals to A? No. Well, that's your answer, why it is not totally ordered. Exactly. Yep. So what Aiden says in the text channel is correct. So I hope that answers the question. Why is less than not totally ordered? Because it is not reflexive. So why less than is not totally ordered is more of a knowledge thing than an application of knowledge thing, because when we defined when we defined totally ordered as partially ordered and also comparable, but when we defined partially ordered, we also mentioned that it requires reflexive, and since we already know it is not reflexive, less than is not. It's not even partially ordered. If it's not partially ordered, it cannot be totally ordered. Besides, we can choose A and B in any way, right? If I choose A to be 2 and choose B to be 2 also, that the requirement that we need one of them to work, ARB or BRA, it still applies when A and B are the same. And, less than definitely would not meet that requirement. So, there's that. Cool. Ooh. Any other questions about this, homework assignment? All right, cool. Yeah, that makes that I'm glad. So the homework assignment is kind of my way of making sure that you guys understand the concepts by giving you kind of something to think about. So I'm not asking for definitions, because you can easily just look it up. I mean, that's not worth any points in this class, just to be able to regurgitate something. But I want you to apply the definitions and kind of figure it out by yourselves and go like, nope, not this one, but yes to that one, and so on. And if you do not get a perfect score, it's not a big thing, okay? Because all the homework assignments only add up to what, 20% of the percentage of this class, so it's not really a whole lot. I mean, it's not zero either, okay? I wish I could make it zero, but I think a lot of people would complain. But it is not the majority. So for people who did not get a perfect score, it's okay. If you did this by yourself, you did not ask anyone else, and this is all based on your understanding of the material, the homework assignment is just telling you that, well, you may have forgotten about this, okay, or you may not have thought about that, and so on. So it's basically just a feedback mechanism so that you go like, okay, now I get it. So that's kind of how I look at the homework assignments. All right, so now we can move on to this thing here. Yeah. All right. So we were on the second one, and then we move on to the third one. So from the first line to the second line is the application of De Morgan's law, and then from the second line to the third one is uh, no, this one is De Morgan's law. From the first line to the second line is no, that's De Morgan's law, and then from here to here is um, another De Morgan's law. Yep, that's another De Morgan's law. So we are converting this thing here into this thing over here. So De Morgan's law works in two different ways. I'll explain that in just a little bit. And then from here to here, we are using we're using the reverse of simplification. I suppose you can call it unsimplification, desimplification, complication, or whatever, right? It's actually called the rule of identity, okay? Because anything and true is whatever that you start with. So I just introduce phi and true, and then row and true to replace phi row by themselves. And then over here, I use complication or unsimplification again. We basically look at true and go like, what else can we talk about true, right? So true is anything or the negation of that anything, right? Because one or the other one has to be right, has to be true. So, so I turn this one into just psi or not psi, and then the other one too. And then from here to here, I applied distribution again. Not exactly FOIL, okay, because the other side only has one single thing, but it's distribution. And then from here to here, I used this term for this, factoring. That's it. So from here to here, I used factoring, because I find that, hey, there's one not phi and not psi, and then over here we have a psi and not psi, okay, right here. So we have a phi and not psi. So I used factoring, just like you would use factoring in normal algebra, but this is applied to Boolean algebra. So I use factoring, and then this is also factoring. After the factoring, I find out that, hey, we are grouping not phi or phi, into one single expression. So that is simplification. So it simplifies to true. Same thing with row or not row. That simplifies to true too. So now we have phi, not psi or psi left. And that is simply true. But if you have a gigantic OR expression and one of the components that you're ORing is true by itself, then the whole thing is true. Forget about the rest. The whole thing is true. So that's kind of how this proof works. Okay. Now, if you ask me, is this the simplest way or the smartest way to prove this particular theorem? I don't know. I mean, this is just one way to do it. Okay. And the whole point is it can be done. So, so what does that mean? That means this implication is always true. Okay, doesn't matter how you choose your phi, your psi, or your row, this implication is always true. So that makes it a good candidate as a production, which is a syntactic manipulation thing that we use in propositional logic. So that's why we basically end up with this thing here. If you can find me a disjunction, phi or psi, and find me another expression where it has the negation of one of these two components. So in this case, I just use psi, so it has the negation of psi, or rho. So this means phi and rho they can be related. They may not be related. It doesn't matter. Okay, all that matters is we have psi, not psi. Psi is in one, not psi is in the other one, and we have two disjunctions. That this is infers, right? So that infers a new expression. So the new expression or the new well-formed formula is that phi or rho. So what is cool about this is we get rid of a component because psi disappears after the inference. So that is really, really cool. Okay, so why is this so cool? We'll see later. I'm looking at the clock. We got we got more than half an hour, so we are making good progress today. Excellent. Unless you guys have questions. So to counteract my coffee, you guys will have to start to ask questions, because that will uh, basically make the class go a little bit slower, at a normal or acceptable pace. Because if you don't ask questions, I would kind of make the assumption that you guys are getting everything already. All right. I'm still not seeing any questions, so I'm continuing with my current pace. In fact, I'm gonna give you guys a little bit of time to ask questions, and I'm gonna drink my coffee. Still no questions. All right, so moving on. So we are moving on to redefine, what we see as a well-formed formula. In other words, we are only taking a subset now of what used to be considered a well-formed formula. We take all of those well-formed formula and go like, this is too general. We'll restrict to a smaller set. Okay. Now extending, well-formed formula to consider something that wasn't a well-formed formula before, that may not be a very good idea. But restricting, if it works, it's okay. So we are now restricting so that omega 1, which is the set of operators or what we call connectives, only has negation, just like before. Okay, we only got one item in omega 1, even before. So that's not a big deal. The second one is we also want to redefine omega 2, and this time only to have OR. In other words, I got rid of a whole bunch of stuff, right? Implication, gone. Conjunction, gone. Is equivalent to, which is if and only if, gone. Okay, so we only got one single thing left, which is disjunction. And we'll also change the way we define is a well-formed formula by introducing this new predicate, which is a disjunctive element. Right? Is a disjunctive element for all e in alpha. So A, what we see as uppercase A is actually alpha. So everything in alpha by itself is automatically known as a disjunctive element. Okay, so that forms the base case. So now we look at the other is a disjunctive element. So if you look at everything in alpha, the negation of that thing is also considered a disjunctive element. Okay, so these two rules. Okay, these two rules are fairly easy to understand. It simply means if you take anything from alpha, that is a disjunctive element. If you negate anything from alpha, that is also considered a disjunctive element. Okay, so at this point, this disjunctive element is simply pick anything. Okay, pick a thing from alpha, that is a disjunctive element. And if you pick anything from alpha and you decide, but I want to negate it, well, that's okay. It is still considered a disjunctive element. So now we move on to is a well-formed formula. Okay, what is considered what is considered a well-formed formula in this case? So I use quantified notations, simply because I don't know how long your disjunction is. Okay, so we'll basically this is just my way of saying, let's say you have a disjunction. Let's say you pick. Okay, this is the other way to say it. Let's say you pick n items. Okay, each one is a disjunctive element. Okay, which means each of these phi I is either an element coming from alpha or the negation of an element coming from alpha, and we have n of these things. Okay, so the disjunction of all of these phi's is a well-formed formula. That's how we redefine is a well-formed formula. It is not even recursive anymore. Okay, you cannot nest things anymore. So a well-formed formula is basically a disjunction, can be potentially huge, gigantic disjunction of things, and each thing in the disjunction is either an element from alpha or the negation of an element from alpha. So that's the verbal way of describing what is now considered a well-formed formula. So let's go take a look at some examples, because I think examples always help a little bit. So we switch to the tablet, which has fallen asleep already, and I just woke it up. So let's say alpha has, okay, the constants, right? And then we have P, Q, R. Okay. The Greek letters are kind of, yeah, they're sort of in alpha, but we don't use those. We don't consider the Greek letters to be usable in a well-formed formula, okay, because they're only used when we try to specify the transformation rules, the productions. Okay, so we consider alpha to be just 0, 1, and then PQR. So that means P by itself is a well-formed formula. Not Q is a well-formed formula. P or not Q is also well-formed. P or not P, which is not very useful, is also well-formed. Then what is not well-formed, Tech? The negation of P or Q is not well-formed. Okay? Because the negation is no longer applied to just one of the things from alpha. So that's why it is not well-formed. What about this? Okay, or P or Q or R. This is well-formed because using using the associative law, we can remove the parentheses, because this is really the same thing as without the parentheses. So, whoops, I said without. Yep, there we go. Okay, so it is still well-formed. So are we understanding what is now considered a well-formed formula? It is a very small subset of what it used to be, but it's okay. It's just that you cannot negate anything unless it is just one thing coming from alpha, and you cannot use any other operators. That's basically the rule. Are we good so far? Any questions? I'm just going to finish the rest of my coffee now, so that you guys get some time to ask questions. I'm not seeing any questions. Okay. Then we're going to move on. Now, one thing we have to remember is all the well-formed formulae that are known to be true, they're all ended together. Okay, so let me give you a more visual representation. All right, so let's just say that this is the space of all the well-formed formula, and now we can actually put it in as a box, because by using this restriction, now we have a finite well-formed formula space. Now I have to use some tricks, like the items inside the disjunction, they have to be sorted in a alphabetically increasing order, and so on and so forth. Okay, so we basically look at P or P and go like, no, that's just stupid. Let's just call it P. So by using all of these simplifications, the well-formed formula space is now contained. It is finite. So now we say, we have a few things here, from omega, from iota. That's right. And then we go through resolution a few times. Okay, so these two resolve into this, and then these two resolve into this, and so on. But all of these things are true at the same time. So that means, if I call this one alpha, this one is beta, this one is gamma, and this one is delta. How do you write delta? What is the lowercase delta? I suppose I can just look it up. Is it D? Oh, that's right. I think it's Is it like this? Curvy D? Okay, I can just look it up. I'm just looking over the side. You guys can use LaTeX. Oh, I can use LaTeX. Stupid me. I hate it when I, forgot about the obvious, because I can just type LaTeX here and then have MathBot to find out what delta looks like. There we go. And then we have, epsilon, gamma, What will be the next one? We just use theta here. Okay. So now we have these well-formed formula that are known to be true. I don't really care exactly what they are, what they look like. But the truth is, they're all true at the same time. So that means, alpha and beta and gamma and delta and theta, this conjunction is true. Okay, because if I know individually these things are either in the set iota or they are inferred by applying the rules, then I can say, if I make a long, huge conjunction with everything that is either known to be true because of iota or eventually known to be true because of the application or the repeated application of the transformation rule in zeta, then if I make one gigantic conjunction out of it, that conjunction is still true. Okay? So do we have any questions about that? Okay. Oh, but tech, doesn't that mean that because under the new uh, rule, each one of these, okay, is one gigantic disjunction. Okay, so alpha is one gigantic disjunction, beta is a disjunction of something of some kind, gamma is a disjunction of something, and so on. So that means this is a gigantic conjunction, and each component can be a gigantic disjunction, right? Yes. Okay, so that means if you want to draw this as a syntax tree, and it's going to look like this. Okay, you just have a whole bunch of disjunction stuff, as one single disjunction expression, another one, and then another one, and then all of these are ANDed together. That is what we are talking about. Okay, so we have a conjunction of disjunctions, and there's another name for these things. This looks like a three-fanged smiling vampire with two hands. These two are the hands, right? This is the mouth, and these are the fangs, and these are the smiling eyes of the vampire. Anyway, this is called CNF, for conjunctive normal form. Okay, so CNF stands for conjunctive normal form. All right. So let's go back and see what each thing can be. Okay, so I'm just going to backfill this thing here a little bit. So we can have P or not Q or R or S or not T. And over here we can have Q or R or not S or T. And then over here we can have, I'm just giving you an example. Okay, so it's totally randomly picked in this case. Okay, so we can have P or not Q or R or not S or not T. So now we have, each one is a disjunction, and then we just have a conjunction of the disjunctions. Okay, that makes a CNF. Okay, this is just a random example of what a CNF looks like, a conjunctive normal form. So are we good so far, or do we have any questions? I guess no questions other than I'm still not seeing a smiling three-fanged vampire in this picture. That's okay. That's not going to be in the quiz. Alrighty. Okay, so now we have to draw a relationship between conjunctive normal form and resolution. How do these things relate to each other, right? So CNF, let me go back to the tablet. A CNF looks like this, okay? It is uh, overall, it is a conjunction of things, and then each thing in the conjunction is by itself a disjunction, and then in the disjunction we can only have elements from alpha or the negation of an element from alpha. So we can just, those are the restrictions. And what does it have anything to do with this resolution? What do you think? Well, phi can be, a disjunction of things by itself, and then rho can be a disjunction of things on its own, and then psi is something from alpha, and since psi is already something from alpha, not psi is also going to be, the negation of that, right? So that means if I express everything in CNF, that makes resolution pretty easy because it everything is already in the form that is ready for resolution if I can find one disjunctive thing to have one particular thing and then another disjunctive expression has the negation of that, then I can apply resolution and get rid of that variable in the process. That is why CNF relate to resolution. Because I want you guys to understand why we have resolution, which looks like, okay, we just know that this implication is always true, okay? And then we talk about CNF, but how do they relate, right? So this is why they are related, okay? Because CNF makes it possible to apply resolution again and again. Now, it all depends on what type of disjunctive expressions you have, but if you have the right ones where one contains the non-negated element from alpha and then the other one contains the negated version of the former, then we can apply resolution. Now, resolution simply means take the rest of each one, concatenate them together, and then we have a new expression that is also known to be true. Okay, that is what resolution does. Okay, so now the question is, isn't this a little bit restrictive? Okay, because we want to be able to express everything using CNF. In other words, if I give you a random, Boolean expression that is by itself well formed, okay, can we transform that into CNF? Because if the answer is no, then we have a problem, don't we? Because this system is no longer complete in the sense that it cannot even represent all Boolean expressions that we used to be able to. So as it turns out, the answer is yes. Okay, we can turn any syntactically correct Boolean expression into a CNF format. And then somebody's gonna say, are you really sure? Even if it has nesting, like conjunctions nested in a negation, and then the whole thing is inside an implication, and blah 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 blah. Yes, even that. So the next item that I want to show you is not so much the rules, but I want to show you an example because the example is an application of the rules. So I think that's easier to get through. So this is the original expression. As you can see, it has quite a few nesting and has got implication, has got a negation applied it to an implication, and so on. Let's see what we can do with this. Okay. Now this time I'm just reading from my notes, but I have to kind of recognize from my notes, what I am doing in each step. So from step 1 to step 2, I'm getting rid of the implication. So R implies Q becomes not R or Q. That's just the definition of implication. From the second row to the third row, I applied De Morgan's law, which turns a negation of a or into just a regular AND by negating each side of the original disjunction. And then from here to here, I applied simplification. The negation of the negation of the negation of R is just R. And then from here to here, I applied distribution. So I did not use. Let me think about this. Right. So this is just distribution, and then from here to here, this is distribution again. So this is like the 3-item version of FOIL. Okay, so it's a because FOIL is kind of like Cartesian product, right? So when you have 2 items and 2 items, you basically just pair up each possible way. So when you have 3 versus 3, it is kind of the same thing. So think about in normal algebra, you have a plus b plus c, the whole thing, times x plus y plus z. Okay, so you end up with 9 products that are added together. Kind of the same thing, same deal here. But it applies even when you have overall a OR operation, and then the sub items that we are ORing are conjunctions. So we just end up with 9 terms here. And then of the 9 terms, I also do the OR with the outside. So basically I use distribution again. So we end up with a gigantic long expression like that. And some of these can be simplified. Okay, so let me show you what simplification is being used here. When you see R or R, well, that just simplifies to R. Okay, so that's an easy one to simplify. When you see something and the negation of itself in an OR, that simplifies to true. So when we have not P or P, that simplifies to true. Doesn't matter what the rest of the OR has. So that simplifies to a true. This also has not P or P. This one also has not P or P. So all of those simplify to just simply true. So now we end up with this expression here. So now we have to see how this one simplifies to this one over here. How do we get rid of not P or R or not Q? Or how do we get rid of not P or R or T, and so on? So that simplification has to do with if you have one OR expression that has fewer components compared to another OR expression, the one that is more general, which means the one, excuse me, I take it back. And both disjunctions are in the same conjunction, you can get rid of the more general one. Okay, so I know this is not making a whole lot of sense. So let's go through algebra, Boolean algebra, and you might want to time mark this, okay, because this is something that you might need to refer to or copy on to your own notes, okay, eventually. So let's switch over to the tablet, okay. And we're going to go through some basic stuff in Boolean algebra. So the basic stuff in Boolean algebra, since we only have to deal with OR, right? So we can say A or B is the same as B or A. Okay, that's it's commutative. Okay, disjunction is commutative. That's fairly understandable, right? And everything in Boolean algebra can be proven using a truth table. So so you can just go ahead and use a truth table if you want to. And then another one is A or B or C is A or B, the whole thing, or C. This is associative. So these are fairly simple stuff that we kind of know already. And then we get to, let's do simplification first, okay? Or identities. A or false is just A. A and true is just A. A or not A is always true. A and not A is always false. So do we have any questions up to this point? So these are kind of axiomatic, okay? it's really just like normal algebra, except in normal algebra we have reciprocals, we have multiplication, we have division, addition, subtraction, and so on. And then in Boolean algebra, we only have conjunction, disjunction, and negation, and then the application of parentheses. And then we have this one, which we have talked about many times already. This is just not A. Oops. This is just not A, the whole thing, or B. And now we can move into distribution. So distribution, there are two. Okay, in normal algebra, there's only one rule of distribution. In Boolean algebra, there are two, but they are symmetric. So A, oh, okay, I have to remember not to use the simplified form yet. So A and B or C is the same thing as A and B or A and C. So this one is sort of intuitive. If you think about conjunction as multiplication, and if you think about disjunction as addition, this one is kind of the same thing as its counterpart in normal algebra. The next one is not as intuitive because it does not have equivalence in normal algebra. So with this one, I can also say this is the same as A or B and A or C. So this one does not have an equivalent form in normal algebra. Okay, so this one is sort of special by itself. All right, so let's move on to even more fun stuff. Let's talk about De Morgan's law. There are two De Morgan's law. So one way to look at De Morgan's law is it is quote-unquote the distribution of negation. Okay, that's one way to look at it. So if you have the negation of A and B, it is the same thing as not A or not B. It also works the other way around. If you have the negation of A or B, it is the same thing as not A and not B. All right. So do we have any questions about all of this stuff? So these two are called De Morgan's law. Okay, and these two are distribution, or if you look at it the other way, so from left to right, they are known as distribution. From right to left, they're known as simplification or factoring. Okay, so there we go. And then these four, you can kind of lump all of these as some kind of identity, rule. Okay, so you can kind of sort of lump these four. So now let's move on to something that is a little bit more obscure. Okay, so let's say we have A or A and B. Okay, this can be simplified to just A. Does that make sense to you? Because A and B is basically more restrictive compared to just A. Now, A can be a gigantic complex expression, and so can B. So I don't really, so A and B in all of these, rules can be an expression. Okay, but in this case, A is more general compared to A and B. So when we are doing a OR, we keep the one that is more general. Because if A is already true, then the disjunction is going to be true anyway. If A and B is true, then we know A is got to be true. So that means that means it is already covered by having A being true. So the opposite of this is A and A or B. And this also simplifies to just A. Because in this case, in a conjunction, we can remove things that are more general. So when you think about A, which is itself an expression, and then you think about A or B, which is a more complex expression, But one thing we know about A or B is it's going to be more general compared to A. So in a conjunction, if A is already true, we know A or B is also going to be true, so it is useless. If we know that A is false, then there's a chance that A or B is true, but it doesn't matter because if in a conjunction, if one component is false, then the whole thing is false anyway. So that makes A or B being a completely useless expression. And you can kind of use this way of looking at things also to look at the first one. If I know A is true, then the disjunction is going to be true anyway. If I know A is false, okay, then we also know that A and B is also going to be false. So that makes A and B a useless expression in the context of this entire disjunction. So this is a really kind of powerful way of simplifying expressions, because it is one of those things that are not really obvious because we are used to traditional or conventional algebra, for numbers and values. But in this case, we are dealing with something that is Boolean, and there are certain simplifications that we can do in Boolean algebra that is not obvious to us. All right. So are we okay so far with all of these things? Any questions about any one of these Boolean algebra rules? No questions. All right. So without any questions, then we have just talked about how we got to from the second last row to the last row here, because we already know that there's a not P or R, and then everything is ended together. So that means anything with not P or R or something are useless. That extra thing here, like T, is useless. And for the same reason, since we already have not P or not Q, so if we have anything that is not P or not Q or something else, like this extra R here, this is also useless. And that's why we can now simplify the entire thing to just not P or R, the whole thing, and not P or not Q, the whole thing. Are we okay at this point? I don't see any questions. All right. So I'm gonna. Oh, okay. Why is the or t useless? I am going to refer. Are you referring to this or t over here? So think about this, not p or r, as a, and then think about t as b in the in one of the last two simplification rules that I used in the tablet. Because these two are ended together, right? So not P or R is considered A, and T is considered P, and then we have a overall conjunction, and each component is a disjunction. So now we are looking at this case here, where A becomes, let me see, not P or R, and then B is T. Now do we see how we just applied the last rule of simplification? Okay, yeah. So that's kind of what the next homework assignment is about, is for you guys to look at these rules, okay, and go like, okay, these are the ways we can twist things around. Think of this as Rubik's Cube, right? So these are the way things can rotate, okay, and then what you want is to start with something that has, all the colors, all over the place, and then you want to twist and turn, the Rubik's Cube back into, okay, we got all the colors, all the same colors on one face of the final cube. That is kind of what we're doing with the next homework assignment, which I think I can assign now because I don't see any questions, and apparently there are no questions. So, all right, roll ROLL. Yes, we're going to take roll, and there are two things that I need to do. One is to take roll first. So we'll go ahead and create the roll thing first. So, and it looks like a quiz, but it's just for roll taking. And I do not use roll taking stuff, for grading purposes. It's just not a good idea. So we'll say this is 2021 3/8 roll taking. And it's all going to be going to roll taking activity. Yeah, I just got a lot of messages. Wait until you see the Discord side. Alright, so we'll go to edit. I'm just looking at the time, this is kind of perfect time for this. And I'll make it due at 1:30. Okay, so that kind of gives you guys plenty of time. Unfortunately, Canvas does not understand today. The date format that it understands, is really limited, and it doesn't even understand 24-hour format. Which is really lame. Alright, so now we get a question. And of course, in my head, I'm thinking about what word should I use this time. Oh, I know the one. I know just the one. Okay. I think in terms of grammar, I think I should change to present continuous tense. There we go. Alright. I think vampire is a good one. So, uppercase or lowercase v is fine. Update question. And then save and publish. There we go. So, vampire. There we go. And on top of this, so go ahead and do the roll taking activity right now as I work on releasing the next homework assignment. Alright, so the next homework assignment is called CNF. And we are going to set up the due date. I will give you guys a week to do this. I mean, that should be enough time if you kind of not procrastinate. But this is one of those homework assignments where if people procrastinate, it's gonna be tough. Okay, if people start to procrastinate. So a week from today is the 15th, and I'll make it due at noontime, which is right before class. There we go. And save and publish. There we go. So now you have the roll taking thing. Take care of that first, okay? Because that has a time limit. And we also have the CNF homework assignment. I do check my messages. When I reply to my messages using Outlook, it does not reflect here as replied. And besides, I handle most of the questions through Discord also. So there are a lot of messages here that are marked, that are unreplied to, but I actually did using Outlook because I don't feel like having to sign into Canvas to do things. All right, so get your roll taking thing done, and I would get started with the homework assignment right away. Because if you do have any questions, you want to bring those questions on Wednesday, and not wait until Sunday or next Monday morning, because it takes a little bit of time to go back to these rules in Boolean algebra and to find out when uh, which one is applicable and which one you should be using. Okay. One trick about this is with the identity stuff, it goes the other way around too. Okay. Most of the time you want to simplify by going from left to right, but very, very occasionally, maybe it makes sense to go from right to left. Okay. And the same applies to all of the other rules. The implication one is always going to be from left to right, okay? Because we are not reverting back from a or back into an implication. So that one is always from right to left. But the other ones, typically it depends on the application. And the objective is to end up with a CNF, a conjunctive normal form. So you got to make sure that you understand what is a conjunctive normal form first before even attempting on the homework assignment. You can always give yourself, a simpler expression to try out first, and not to start with something as complex as the homework assignment. So that's the other thing we can do. All right, so get started with the homework assignment. If you have questions about doing the homework assignment, bring those questions on Wednesday, and I will try my best to explain Boolean expression if there are questions about it. And that's it for today. I will see you guys on Wednesday. I'll stay behind a little bit just in case people have questions, but otherwise I'm going to stop